Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 2.1 on matrix operations. I'll teach you all about how to add, subtract, and multiply matrices, how to find the transpose of a matrix, and how to find the standard matrix of a linear transformation using matrix multiplication. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's begin by learning about matrix addition and scalar multiplication. To add or subtract two matrices, we first need to check that both matrices have the same dimension. That means they have the same number of rows and same number of columns. We then just need to add the corresponding entries. Let's walk through some examples to see how this works. Before we begin, let's look at the dimensions of each of these three matrices. Our A is a 2 by 3 matrix, our B is also a 2 by 3 matrix, and our C is a 2 by 2 matrix. Let's first add A and B, and we can add these matrices because they have the same dimension. We'll begin by adding the first entries. This gives us 2. We'll then add 2 plus 3, which gives us 5. And then we'll add 7 plus 4, which gives us 11. We're going to do the same thing for the next row. We'll add -1 and 1 and get 0. We'll add 3 and 3 and get 6. And then we'll add -5 and 1 and we'll get -4. You might want to stop the video and see if you can compute A minus B. A minus B is just going to be 0 minus 2, which is -2, 2 minus 3, which is -1, and then 7 minus 4, which is 3. Looking at the second row, we have -1 minus 1 gives us -2, 3 minus 3 is 0, and then -5 minus 1 gives us a -6. Let's now compute A plus C. A is a 2 by 3 matrix, and C is a 2 by 2 matrix, and because they're not the same size, we can't compute A plus C, and we say that it's undefined. Let's now learn how to multiply a matrix by a scalar. To multiply a matrix by a scalar, we just need to multiply every entry in the matrix by the scalar. Let's look at an example where we're given A and we're asked to compute 3A. To get 3A, we're going to multiply every entry by 3. Let's begin by multiplying the entries in our first row by 3. 0 times 3 is 0, 2 times 3 is 6, and then 7 times 3 is 21. Let's now look at our second row. 3 times -1 gives us a -3, 3 times 3 is 9, and then our last entry is a -15. Let's now turn our attention to learning how to multiply matrices. Throughout the remainder of this course, we're going to be doing a lot of matrix multiplication. There are two main steps that we need to follow when multiplying matrices. We first need to check that the number of columns in the first matrix equals the number of rows in the second matrix. This will tell us if the two matrices can be multiplied. Let's see how this works when we multiply A times B. If A is an M by N matrix, it has N columns, and then B is going to have N rows. And we'll just make it multiplied by P. This ensures that the number of columns of A is equal to the number of rows of B. The second step that we'll need to follow, and that's going to take all of our time, is to multiply the elements of each row in the first matrix by the corresponding elements of each column in the second matrix. I'll show you how this works by looking at an example problem. We're given matrix A and matrix B, and we're asked to find the matrix AB. Our first step is to see if we can actually multiply A and B. A times B is going to be giving us a 2 by 2 matrix times another 2 by 2 matrix, and we notice that the number of columns of A equals the number of rows of B, so we can multiply them. Our answer is going to be a 2 by 2 matrix. There are two ways that we can notate how to multiply two matrices. Let's look at the first way. The first way is to multiply A by the columns of B. The first column in our product is then A times B1, and the second column is A times B2. Looking at the matrices above, A times B1 is our matrix A, 2, 2, 3, 4, times the first column of matrix B, and that's going to be 1, 2. This is a matrix vector product, and we already know how to compute this. Our first entry is going to be the row 2, 2 times the column 1, 2, and that's going to be equal to 6. And then our second entry is the second row times our column of B, and that gives us a value of 11. Let's now compute A times B2. This is just our matrix A, and now we're going to multiply it by our second column of B. This gives us 2 minus 2, which is 0, and then 3 minus 4, which is minus 1. AB is then AB1 in our first column and AB2 in our second column. This gives us that AB is 6, 11, 0, minus 1. The second way to notate how to multiply two matrices is to look at the entries in the matrix product. An arbitrary entry, Cij, is the ith row of A times the jth column of B. For example, C11 is the first row of A times the first column of B. You do that multiplication, and then you place the answer in the C11 spot. C21 is going to be the second row of A. Remember, the first number is the row of A times the first column of B, because the second number is the column of B. Let's see how this works in our example. We had A was equal to 2, 2, 3, 4, and we were given that B is equal to 1, 1, 2, minus 1. AB is equal to 2, 2, 3, 4 times 1, 1, 2, minus 1. Let's make some space for our answer. To compute this entry, we're going to take the first row of A times the first column of B. That's going to give us 2 plus 4, which is 6. To compute the entry C12, we're again going to take the first row of A, but now we're going to multiply it by the second column of B. That's going to give us 2 minus 2, which is 0. Let's now compute the entries in our second row. The first entry in our second row is going to be the second row of A times the first column of B, because that entry is C21. We're going to have 3 plus 8, and that's going to give us 11. Now let's compute our last entry. We're again going to take the second row of A, and now we're going to multiply it by the second column of B. That's going to give us 3 minus 4, which is negative 1. So our answer is 6, 0, 11 minus 1. And you might notice that this answer is the same as we got looking at the multiplication the first way. Let's now get some practice in multiplying these matrices. In our first example, we have a 3 by 2 matrix multiplying a 2 by 3 matrix, so our answer is going to be a 3 by 3 matrix. I always like to go ahead and do that first because we can see if we can actually multiply the matrices, and then we can also write down the size of our answer. Let's begin by multiplying the first row by the first column. That will give us our first entry. So that's 1 plus 2, which is 3. Now let's multiply that first row by our second column, and we get 3 plus 4, which is 7. We'll then multiply that first row by our third column, and we'll get 5 plus 6, which is 11. You might want to stop the video right now and see if you can get the answers in the next two rows. We'll multiply the second row of our first matrix times the first column of our second matrix, and that gives us a 0 minus 2, so that's minus 2. Multiplying that row by the second column gives us a 0 minus 4. And then multiplying that row by the last column gives us a 0 minus 6. Now let's multiply the last row of our first matrix times these three columns. Multiplying it by the first column, we get 2 plus 6, which is an 8. And then we get 6 plus 12, which gives us 18. And then 10 plus 18 gives us 28. I know this is complicated, and don't be discouraged. You can do this. It's just going to take a lot of practice to learn. Let's now look at our second example. We're going to check the size first. We have a 2 by 3 matrix, and then, we have a 2 by 2 matrix. Notice that these two numbers are not the same. So because of that, we're going to have to say that our matrix is undefined. Let's now look at an example that has a variable in one of the matrices. We're asked to find what value of k, if any, will make AB equal BA. To do this, we're going to first compute AB. We'll put the matrices right beside each other. There's our A, and here's our B. And then we'll go ahead and do the multiplication. A and B are both square matrices, and they're the same size, so our answer is going to be a 2 by 2 matrix. Multiplying the first row of A times the first column of B gives us 8 plus 15, which is 23. And then multiplying that first row of A times the second column of B gives us a minus 10 plus 5k. Now let's multiply the second row of A times the first column of B. That gives us a minus 12 plus 3, which is minus 9. And then multiplying that row by our second column gives us a 15 plus k. Now let's do the same thing for BA. As before, I would suggest you stop the video and see if you can complete this one on your own. We have our B, which is 4, 3 minus 5k, and we're multiplying it on the right by A, which is 2, 5 minus 3, 1. We'll multiply the first row of B times the first column of A, and we get 8 plus 15, which is 23. Now let's multiply that row by the second column of B, and we get 20 minus 5, which is 15. Let's now multiply the second row of B times both of these columns of A. The first one is going to be a 6 minus 3k, and then the second one, we're going to get a 15 plus k. In order for these two products to be equal, minus 10 plus 5k is going to have to equal 15, and minus 9 is going to have to equal 6 minus 3k. Let's set those equal and see what we get. We have minus 10 plus 5k is equal to 15. That means that k is equal to 5. We then have minus 9 is equal to 6 minus 3k, and that also gives us k is equal to 5. We can then say that when k is equal to 5, AB will equal BA. Since there's only one value of k where AB is equal to BA, this problem shows us that AB will often not equal BA. Now that we know how to multiply matrices, let's look at some properties of matrix multiplication. In these properties, we're going to be assuming that A, B, and C have compatible dimensions, meaning that we can add them and multiply them. Our first property is called the non-communicative property. This property tells us that the product of two matrices depends on the order in which they are multiplied, and most of the time, AB is not equal to BA. Our second property is the associative property, and it just tells us that matrices can be grouped in different ways without changing the result of the multiplication. Our third property is the distributive property. We have a left one and a right one, and they just tell us that matrix multiplication is distributive over matrix addition. Our next property involves the identity matrix. We write the identity matrix with a capital I, and the diagonal elements of this matrix are equal to 1, and the off-diagonal elements are equal to 0. Just as a reminder, this is the diagonal. The identity matrix behaves just like the number 1 in scalar multiplication. If we multiply A times I, that's the same thing as multiplying I times A, multiplying from the left, and that gives us the matrix A. We'll be using the identity matrix a lot when we compute inverses of matrices. And then our last property is scalar multiplication compatibility. That just tells us that matrix multiplication is compatible with scalar multiplication. We can multiply a scalar times AB, or we can multiply that scalar first times A, or we can multiply that scalar first times B. There are many applications in linear algebra where we need to compute powers of matrices. Let's look at 3 properties that will help us do that. The first property tells us that A to the K is just A multiplied by itself K times. We need to note that we can only multiply A by itself if A is a square matrix. And the reason for that is if A is a square matrix, we have A times A, and we're going to have an n by n and an n by n. So only when it's square will the columns of A match up with the rows of A. Our second and third properties are just like the properties that you learned in algebra. A raised to the P times A raised to the Q is just A to the P plus Q. And then A to the P raised to the Q is A to the PQ. When you multiply powers of matrices, you first need to check that the matrix is a square matrix, and then you just need to multiply it by itself the required number of times. Let's walk through an example to see how this is done. We're given A, and we're asked to compute A cubed. A cubed is just going to be matrix A times matrix A times matrix A. Let's write these down. We'll just line them up all beside each other. We can multiply these in any order. I tend to prefer to multiply the first two just because I think it's easier to work from left to right. So let's go ahead and let's multiply these first two. We get 2 times 2 minus 5 times 3, and that gives us a minus 11. In our next entry, we have 2 times 5, which is 10, plus 5, and that gives us 15. In the entry in our lower left, we have minus 6 minus 3, gives us a minus 9. And then in the entry in our lower right, we have minus 15 plus 1, gives us a minus 14. We're then going to multiply this by 2, 5, minus 3, 1. And we're going to get, in our first entry, minus 22 minus 45. I'm writing these down because it's a bit hard to do all of this in your head. The next entry on our right, we get a minus 55 plus 15. The entry in the lower left gives us a minus 18 plus 42. And in the lower right, we get a minus 45 minus 14. This gives us a final answer of minus 67, minus 40, 24, and minus 59. Another matrix operation that we'll look at is the transpose of a matrix. The transpose of a matrix is just an operation that makes the rows of the original matrix become the columns of the new matrix and vice versa. Let's look at this example to see how this works. Our A is a 2 by 3 matrix. So that tells us that our A transpose is going to be a 3 by 2 matrix because the rows and the columns just switch. Let's compute A transpose. We can already write down what the size is because we know it's going to be a 3 by 2. The first row of A becomes the first column of A transpose. So that's just 1, 2, 3. And then the second row of A becomes the second column of A transpose. And that's 4, 5, 6. Let's now look at how to take the transpose of two matrices that are multiplied together. We have a property that tells us that the transpose of the product AB is equal to B transpose, A transpose. Let's make a note in red that this is not equal to A transpose, B transpose. You have to switch the order when you take the transpose. Let's look at an example where I'm going to show you two ways to take the transpose of the product of two matrices. Let's make a note that both A and B are 2 by 2 matrices, so they can be multiplied. The first way that we're going to learn to take the transpose of the product of two matrices is to multiply AB first and then take the transpose. A times B is 1, 2, 4, 5 times 3, 1, 2, 4. You might want to pause the video and compute this product on your own just for some extra practice. And we're going to get 3 plus 4, which is 7. Then we get 1 plus 8, which is 9. In the lower left, we get a 12 plus 10, which is 22. And in the lower right, we get a 4 plus 20, which is 24. Now let's take the transpose of AB. The first row is going to be equal to the first column, and then the second row is going to be equal to the second column. The second way that we can find the transpose of this product is to take the transpose of A and B first and then multiply them. From our property above, we know that AB transpose is equal to B transpose times A transpose. Remember, we have to switch them. This is going to be equal to, let's find B transpose first. Let's pull it down so that we can see it again. So B transpose is going to be 3, 1, and then 2, 4. And then A transpose is going to be 1, 2, and then 4, 5. When we multiply these, we're going to get 3 plus 4, which is 7, 12 plus 10, which is 22, and then we get 1 plus 8, which is 9, and 4 plus 20, which is 24. And our two answers are the same. I personally think that the first way is easier because you only have to take one transpose, but either way will work. The last topic that we'll look at can be viewed as an application of matrix multiplication. We're going to see how to find the standard matrix of a linear transformation using matrix multiplication. In our first example, we're asked to find the standard matrix of a transformation that first reflects points through the horizontal x-axis and then reflects points through the line y is equal to x. This example contains two reflection transformations. Let's let the standard matrix for these transformations be A1 and A2. Looking up above, we'll let this reflection be equal to A1, and we'll let this reflection be equal to A2. We now need to find the standard matrix that combines these two transformations. Let's let the first transformation that reflects points through the horizontal axis be T sub 1 of x is equal to A1 times x. The standard matrix that we're asked to find is T of x, and that's going to be A2 times our first transformation, T1 of x. Substituting in T1 of x, this just gives us A2 times A1 times x. This means that our standard matrix A is equal to A2 times A1. A1 is the matrix that reflects points through the x-axis, and that's equal to 1, 0, 0, minus 1. This is one of the matrices that we found in section 1.9, part 2. A2 is the matrix that reflects points about the line y is equal to x, and it's equal to 0, 1, 1, 0. We also found this matrix in section 1.9, part 2. Matrix A is then A2 times A1. This is 0, 1, 1, 0 times 1, 0, 0, minus 1. And when we multiply these out, we get that our matrix A is 0, minus 1, 1, 0. Notice the order that we did the multiplication by. The second matrix is always on the left. Let's now look at an example where we have three transformations. We're asked to use matrix multiplication to find the standard matrix of a linear transformation which first reflects points across the y-axis, then rotates points by pi over 4 radians counterclockwise, and then stretches points vertically by a factor of 2. Our standard matrix A is going to be equal to A3 times A2 times A1. Let's label our first reflection with standard matrix A1, our second with standard matrix A2, and then our third with standard matrix A3. Our A is going to be A3, and that's the matrix that stretches points vertically by a factor of 2. That will be 1, 0, 0, 2. And then we have the matrix that is a counterclockwise rotation. And we'll write that as cosine theta, sine theta, minus sine theta, cosine theta. We'll plug in the pi over 4 in a minute. And then our first matrix is reflection about the y-axis, and that's equal to minus 1, 0, 0, 1. Now let's plug in that our theta is equal to pi over 4. So we have a root 2 over 2, a root 2 over 2, a minus root 2 over 2, and then a root 2 over 2. And this is our first matrix. I'm going to choose to multiply these two matrices first. And that's going to give us root 2 over 2 minus root 2 over 2. And then in the second row, we're going to get a root 2 and a root 2. We'll then multiply this by minus 1, 0, 0, 1. And we'll find that our standard matrix A is equal to minus root 2 over 2, minus root 2 over 2 on the first row. And then the second row is minus root 2 and root 2. I would suggest that you go back and try to work all of these problems on your own. That will help you to master these concepts. Be sure to check out the next video in this series, where we'll learn all about how to compute the inverse of a matrix.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.